says determine the value of rho. So rho is this symbol we often use for the ratio test or the root test. And why do we use rho? Well, rho is a stand-in for r. And if you look at your Greek alphabet, rho and r are the same thing. So r should channel like, oh, it's kind of like a geometric series, right? Yes, that's the idea. So anyways, okay, find the value of rho associated with the ratio test. Oh, that's very convenient. They told us what we should be doing for the following series. And we have, okay, the sum from 1 to infinity, 2n to the 2n over 2n factorial squared. Now, even if they hadn't told us ratio test, we know this would be a ratio test type question. What gives away it's a ratio test type question? Yes, the factorials. Now, our goal is not to say converge or diverge. Our goal is to say what's the value for rho. And we have some options. Rho is 0, rho is a fourth, rho is e squared over 4, rho is e squared, and rho equals infinity. Do we have an answer? Do we have a guess? You have a 1 in 5 chance.
C.
C? Okay, now you have a 1 in 4 chance. It's not C. Sorry, what? D? 1 in 3 chance, not D. Your odds are pretty good. It's A, B, or E by a process of elimination.
B.
B? It's not B.
E.
E? It's not E. It is A. You nailed it. Yes. Good. Good. And I will say, you can get rho to be 0 or infinity, and you want rho to be 0. That is a desirable outcome. In the future, you'll be like, I want rho to be 0. And we'll tell that story maybe this week. So, okay, what's going on? So we're taking our ratio test. So we're taking the ratio of the next term over the current term. And we don't have to worry about absolute values. Everything's positive here. We say, okay, great. Well, to get the next term, we replace everywhere where there's n by n plus 1. So I just put n plus 1 everywhere where there was originally an n. And then I just copied the term, but I flipped it upside down. So that's the 1 over a sub n. All right. Well, now what do we do? Because we have factorials, the reason we do the ratio test is because we can pull terms off the front of the factorials. So this is really 2n plus 2 factorial. And so I can pull off a 2n plus 2, pull off a 2n plus 1, and then I have a 2n factorial. And similar, I have a 2n plus 2 to the power of 2n plus 2. So I can think of that as 2n plus 2 to the 2n plus 2 squared. The factorial terms cancel. That's good. That's why we did the ratio test. And then we say, okay, what else cancels? Well, notice you have a 2n plus 2 squared and a 2n plus 2 squared. Those cancel. So you're left with a 2n plus 1 squared downstairs. And then this 2n plus 2 to the 2n over 2n to the 2n. If you cancel off all your 2's, that's 1 plus 1 over n to the power n squared. Well, we know how to do that kind of limit. The inside, if we refer to our formula sheet, that goes to e. So we're going to e squared. And that's why there's a tempting e squared floating around. And then here, well, this is 1 over something big. Well, that goes to 0. And e squared times 0 is 0. Now, you might say, well, where would you have gone the fourth from? Well, if you forgot to square here and just said, oh, 2n plus 2 and 2n plus 1 and not the squares, you would have ended up with e squared over 4. So be careful. Be careful. All right. So that's the answer. Any questions on this one? All right. Well, our thought for the day. Life is not linear. You have ups and downs. It's how you deal with the troughs that defines you. And I just was looking for something just to say as sort of a related to today, up and down, up and down. But this is also true. You will have good days, you will have bad days. The bad days don't define you. Don't judge yourself by the bad days. Do the best you can and keep going. You can do it. Well, what's our goal for today? We have one more test. And it's one of the easiest tests to talk about. It's called the alternating series test. The alternating part means we alternate sign. Plus, minus, plus, minus, plus, minus. So this is very different from the previous test we've been talking about for convergence, because in the previous test for convergence, we've always been thinking like, oh, I have a bunch of things that are positive being added up. Here, we're sort of jumping back and forth, adding, subtracting, adding, subtracting. So how does the test work? It says, well, suppose you have a sequence, and let's just drop the plus minus for a second. We have a sequence of terms. If they go to 0, decrease to 0, so they're monotonically going to 0, then the sum converges. So the test is super easy. You just say, hey, do I alternate? Do I go to 0? I converge. That's it. Now, if you think about this, one of the things we've been talking about is that convergence is often tied to how quickly you go to 0. There's none of that here. I can go to 0 very slowly, and still converge as long as I'm alternating. Of course, it leads to some interesting, somewhat paradoxical things happening, but we'll get to that in a little bit later. Okay, so that's our last test. Now, there's a couple things we can do. Because of the way things work, we can easily find the error bound if we have an alternating series. So if we have something where we have this plus minus behavior going on, then what we can do is we can say, how close are we to the final answer? And it turns out, if you go up to a certain point and stop, then the distance you are away from your answer is at most if you went to the next term. We'll see why this makes sense pictorially in just a moment. So that's what we have. If you, L is your total sum, and you say, go up to some place and stop, how far away you are is at most the next term, and that is on your formula sheet. So this shows up on your formula sheet here. Ah, my goodness. We're running out of things we haven't talked about on the formula sheet. Ah, good times. Now, because we have this alternating series, we are going to be in the situation where we want to talk about convergence. And we're going to have two types of convergence. One is absolute convergence. And absolute convergence says, I don't need any negative signs. In other words, if I take the absolute value of the terms, I converge. So that's a very strong type of convergence. We prefer absolute convergence. Conditional convergence says the sum converges, but if I just take the absolute value of the terms and add those up, they diverge. So somehow I need the negatives in place. I can't just add up the terms positive. And so you will see, and this is something that you will almost surely be tested on, absolute versus conditional. Make sure we understand the difference. Absolute is the better one. Okay. So let's put up all our tests. So these are the tests that you'll need to know. Now, unfortunately, we don't have space on the formula sheet to put all these on, so These are things that you'll have to learn. Bits and pieces are on there, but not everything. So we have the nth term test, which says if the terms don't go to 0, we diverge. And I put the alternating series test right next to that because it's somewhat similar. The alternating series test says if your terms do go to 0 and you have this alternating piece, it converges. So the nth term test and the alternating series test are very easy tests in terms of, hey, what's the behavior of the A sub n? We have the integral test, which says you can tie an integral and a sum together as long as you have something which is decreasing. This is a very limited test in some sense. It's mostly used for p-series. And so on a side note, I didn't put it down on the page because I ran out of space, but make sure you know your p-series. Maybe we can squeeze it in. We have enough space down here in the bottom part, right? We'll just add it in. So if I took the sum, k to infinity, 1 over n to the p, when does that converge? What? Yes. This converges if and only if p is greater than 1. And since we have space, the sum, n equals k to infinity, a r to the k, when does that converge? R is small, yes, converges when r is small, positive or negative. Ultimately, these are your two go-to series to do things with and compare things with. So the integral tests, the big thing about that is it gave us p-series. It also gives us things like 1 over n log n. Your basic or direct comparison test says, well, I want to just compare the series to something, either a little bit above it or a little bit below it, which is simpler to work with. If I want something to converge, I say I have to find something above it that converges. So if I want a sub n to converge, I have to find a b sub n above it, which converges. If I want to find something or show something diverges, I say, well, I want the bn to diverge. I have to make the an diverge. I have to find something below it. This can be a little bit difficult to work with, but you do need the comparison test, the way we've talked about things so far. So if you remember the multiple choice problem, 1 over 3 plus sine of n to the nth power. That really needs a comparison test based on the tools we have. We have the limit comparison test, and this one, I like to call this one, get rid of the noise. Because the goal of the limit comparison test says, let's just strip away everything except the dominating terms, and let's understand what's going on with that. So you get rid of anything that has slower growth. So if you see lots of pluses and minuses, limit comparison test is the way to go. Ratio test and root test are nice because I don't have to come up with another series. Both the comparison test and the limit comparison test says you have to come up with another series and do some comparisons. Ratio test and root test are just say, let's compare the series to itself and ask the question, if you were a geometric series, what kind of geometric series would you be? And you figure it out by saying, well, let's look at the ratio of consecutive terms, or let's look at the nth root of the nth term. And then, depending upon what that value is, whether it's above 1 or below 1, tells us whether or not we converge. And, okay, that's our test. And we'll practice that more next time. All right, any questions about the test? Cool. Well, let's talk about our test for today, the alternating series test. Again, we have our terms going to 0, and we say then if our terms go to 0, decreasing, so I can't have my terms go up and down, they really do need to be monotonically decreasing. Then the sum negative 1 to the n, an converges. Okay, so how do we think about this? Well, one way we can think about this is what's going on when we add numbers? Well, what's going on is I have the number line. If I add a positive part, that's a move to the right. If I add a negative part, that's a move to the left. So in some sense, there's the size of the number. That says how far to move. Add, go to the right. Subtract, go to left. So if I start with the term, then I subtract, I move to the left. If I add, I move back to the right. Now, because the terms are decreasing, how much I move to the left is going to be less than how much I move back to the right. What does that tell us? It tells us that we're going to be drifting downward if I take every other term. So I'm from the right side, I take 2 steps, I'm a little bit lower. Take 2 steps again, I'm a little bit lower. And so I'm moving down on the right-hand side. Same idea. If I take 2 steps, I'm going to be moving up. I'm drifting up. So I'm moving in. I'm circling around this limit. And because the steps I take keep getting smaller and smaller, eventually these are going to come together. And one nice intuitive thing is every time I add or subtract, I always jump over the final answer. So it's this idea of sort of cycling in, get to L. That's the idea. Now you can make things a little bit more rigorous. It's monotonic convergence theorem again. But the idea is you just keep jumping back and forth across L, but you're taking smaller and smaller jumps. So eventually you're going to get and stay close to L. All right, that's the idea. The test itself is very simple. And because of this jumping over L, then we say, well, hey, if I stop my sum at some point, then the next step would take me past L to the other side. So the distance between the total sum and then stopping at one point is at most the next jump I make. So that's how we get the error bound. All right. That's the idea. It's a nice idea. I like that idea. Well, here's some sums. We can try these out. 1 over n squared. Will that converge or diverge? And how do we know? If I sum 1 over n squared, does that converge or diverge? How do we know? It converges. Good. How do we know it converges? Right, it's a P series with P equals 2, and it turns out, true story, 2 is bigger than 1. Okay, the next sum, negative 1 to the n over n squared. This is not a P series because of that negative 1 to the n. So we can't use the integral test on this series. Does this series converge, and how do we know? If only we had a test available that could help us with these kinds of series. Oh, it's an alternating series because of the negative 1 to the n. So once we see an alternating series, our next question is, do the terms go to 0? If I divide by n squared, am I going to 0? Yeah. So this converges. And this is by the alternating series test. Okay. Well, let's go to our next batch. The sum of 1 over root n. Do we converge or diverge? How do we know? Diverge, okay. How do we know? It's a p-series. What's p in this case? 1/2. P-series with p equals 1/2, which is less than 1. We could even say less than or equal to 1. Okay. Well, let's look at the next sum. Negative 1 to the n over square root of n. Do we converge or diverge? And how do we know? So what was that?
Diverging using the alternate series test?
Well, alternating series test doesn't have a diverge option. Alternating series test only has a converge option. Can we use the alternating series test here? Yes, because there's this minus 1 to the n. So once we see alternating series, what do we need to ask ourselves? Do we go to 0? Does 1 over square root of n go to 0? Yes. So what's true about this sum? This converges. Alternating series test. Now, if we wanted to, we can even expound on the alternating series test. You could say, well, 1 over square root of n goes to 0. So just like up above, we could have said, 1 over n squared goes to 0. So even though when we don't have the alternating part, it diverges, when we throw in that alternating part, now it can converge. And it can get much stranger. Okay, 2 more. If I add up n, so I add up 1 plus 2 plus 3 plus 4 plus 5, does it converge or diverge? Diverge? How do we know? Diverge is the correct answer, but how do we know that? What's the test? What test allows us to say this diverges? The nth term test. What does the nth term test say? Well, the nth term test says, look at the nth term. And so the nth term test says, well, look, limit as n goes to infinity of n, that's the nth term. Well, that's not 0. So it turns out if you take the numbers 1, 2, 3, 4, 5, ... it's not going to 0. So it has to diverge. But wait, now we'll throw in the alternating part. Sum. Negative 1 to the n times n. Does it converge or diverge? And how do we know? If it converges, why would it converge? It is alternating, but what needs to also be true? The terms need to approach 0. Do the terms approach 0? No. So the alternating series test can't be used here. But wait a second, we just said the terms don't approach 0. So does that give us a clue? So does this converge or diverge? It diverges because nth term test. And that's just as, take the limit as n goes to infinity, negative 1 to the n times n, you're still not going to 0. All right, so we can have all sorts of things happen. Well, maybe not all sorts of things, but some sorts of things. Any questions on these ones? We'll get a lot more practice with these kinds of questions next time. We'll have a lot of fun. All right. Which of the following sums converge? And keep in mind, because I'm the one asking it, the answer may be neither converges. It might be both converge. So be careful. Which one do you want to talk about first? Top one? Okay. Well, what do you see? Negative 1 to the n? Well, negative 1 to the n plus 1 is like negative 1 to the n. What does that tell us about this series? Well, when you see negative 1 to the n, we think what? Alternating. That's like plus, minus, plus, minus. So after we see alternating, what should our next instinct be? Look at the term attached to it. Log of n plus 1 over n. And what do we want to be true about that? N plus 1 over n needs to do what? Go to 0. Does it? Does log of n plus 1 over n go to 0? So if we look at this part, that's the same as log. If we just divide the n, 1 plus 1 over n. What's happening to 1 plus 1 over n? The inside does the following. It goes to 1. Log of 1 goes to 0. So we are alternating. We go to 0. What's the conclusion? Converges. So this converges by the alternating series test. Okay, cool. Now let's look at the second one. Almost the same, suspiciously similar. The sum from 1 to infinity of negative 1 to the n, sum from 2 to infinity, negative 1 to the n, log of n plus cosine pi n, divide by n. All right, do we converge or diverge? What do you think? Does anything make you suspicious here? And we can, by the way, give a definitive answer. This is not like a, well, we'll never know. It's like, no, we know. We can answer this. We have the technology.
Because it's going to be 1 over cos of n. The cos is bounded.
I see a hand up. Does it converge? Maybe. Can you tell me? Why does it converge?
Because cosine to pi over a number of 1, so it's still 1 plus 1 over n.
Is cosine pi n always equal to 1?
Negative 1 over n.
Okay, so it's 1 or negative 1. All right, it's never big. I agree with you there. Certainly it's not big. So you're probably telling me right now that this log goes to 0. You're true. That's right. It does go to 0. But that doesn't mean it converges. I mean, this is meant to, well, I don't want to say trick you. It's meant to have fun. Ha ha ha. Tricking sounds like I'm trying to be mean. What's true about cosine pi n? Maybe we should make a note here. Is there another way to write cosine pi n?
Negative 1 to the n.
It's negative 1 to the n. So when you see a cosine pi n, they're really trying to hide a negative 1 to the n. And at this point, you're like, okay, whatever. More negative 1s to the n, the merrier. So 2 to infinity, negative 1 to the n, log n plus negative 1 to the n over n. Great. So how would that change our answer? I mean, we still have something going to 0. We still have that sign plus minus going on in the front. So why am I hesitant? Is this really an alternating series? Maybe we just want you to think it is, but maybe it's not. What?
What are these mind games?
Okay. So this is the sum, n equals 2 to infinity of negative 1 to the n log. And I'll do the same thing up here. I divide by n of 1 plus negative 1 to the n over n. Now, we're going to take a slight detour for a second. This will, there's a reason we're going to take a detour. Let's channel our inner Calc 1 student and say log of 1 plus x. What does that look like? Well, if you were to graph it, it has a vertical asymptote at negative 1. And it passes through the origin. Something like that. Imagine you were a Calc 1 student. What would you want to do? What's the favorite thing for a Calc 1 student to find? Derivative and tangent lines in particular. We love tangent lines. What's the tangent line at 0? Well, I go through the origin, so all I need to know is the slope. So if this is my f of x, f prime of x is 1 over 1 plus x. So f prime of 0 is 1, which means my tangent line is y equals x. Now at this point, you're like, okay, cool. How does this help us? Well, what's true about minus 1 to the n over n? Well, lots of things are true, but the real thing that's true is that this is going to be small. In other words, it's something near 0. Now, if I have a function near a point of tangency, it behaves like the tangent line. So log of 1 plus x is about x when x is about 0. So when I'm near 0, log of 1 plus x is about x. So what does that do? Well, it says that this is approximately, and when I say approximately, it gets better as n gets bigger. Because as n gets bigger, this gets closer to x, you get a better approximation from the tangent line. And we care about what happens eventually, because it's in the tail. The tail gives us convergence. Okay, so negative 1 to the n times negative 1 to the n over n. Right, 1 plus x. There's my x. What happens when you multiply two negative 1s to the n's together? It just becomes, they cancel out. So what's happening is it looked like an alternating series, but because we hid that cosine pi n there, it turns out it's not an alternating series. And it behaves like 1 over n. Okay, so if the terms behave like 1 over n, do we converge or diverge? we diverge. Now, strictly speaking, what's the test that gives it to us? We've waved our hands a little bit, but if we give the name to the test, it'll be like yes, and this is the hand waving you do. So, well, it's not p-series. That tells us when our n diverges, but how do we get from this to there? What kind of thing are we doing? Sorry, what? Well, I have something else in mind. We have some time. We can play a quick game, right? Okay, so what am I thinking of? E. Okay. T. F. I think someone's trying to sabotage you with an F. Oh, limit comparison test. Oh, you guys got it. Good. Now to find out if I counted my spaces right. Nice. I got the right number of spaces. Good. Limit comparison test. Because what we were doing is we were trying to say, what's the growth? Try to simplify the expression. And so if you have complicated expressions, you say, well, how is it behaving? What's it really doing? That's limit comparison test arguments. All right. So there we go. So be careful. The punchline is keep your eyes out for this cosine pi n, because it can be a little bit subtle. Okay. Any questions? All right. Well, we should practice with the error bound. Find a partial sum n equals 0 to infinity, -1 to the n over 2n factorial, which is less than 0.0001 away from the true value. Now, this will converge, alternating series, and we're dividing by something which gets big. So we know it converges. Say we just want to get an approximate value. How far do I have to add to get something which converges? Okay. Well, what's the idea? If we look up our formula sheet, we can say, hey, there's this nice handy formula in the formula sheet. So sum I equals, I'll put K. Now I'm going to change my notation. K, n equals K up to capital N of -1 to the n, A sub n is less than or equal to A n plus 1. Okay, so we want to be 0.001 away from the true value. That says this part, we want this to be less than 0.001. So what is it we need to figure out? How do we look for it? If we want the left-hand side to be small, we can make the right-hand side small. So the goal make this term small. Now, as soon as I know what term is small enough, that tells me where I stop my sum. What is A sub n in this case? If we have this partial sum, what does the A sub n correspond to? Yeah, it's the part that's not the alternating part. It's the 1 over 2n factorial. So we should write down some terms. Now 0.0001, that's 1 over 10,000. So let's look at our terms. A0, 1 over 0 factorial, also known as 1. Okay, we're not quite there. How about A1, 1 over 2 factorial, also known as 2. Okay, still not there. A2, 1 over 4 factorial. Anybody know 4 factorial off the top of their head? Sorry, what? 24. Okay, are we good? Is that enough? No. How about A3? 1 over 6 factorial. How about 6 factorial? Do we know what that is? 120 is 5 factorial. 720 is 6 factorial. Okay, are we good? No. Okay, how about A4? 1 over 8 factorial. Now, I'm not going to expect you to know this. It's 40,320. You know, because once you get old, you start memorizing factorials. So that's 8 factorial. Is that good? Yes. Yes. Because what happens is that 1 over 40,320, that's below 1 over 10,000. That means we're going to have our error is going to be small if we stop where? How far does my sum need to go? I need to go from 0 up to what number? All right. I've heard several people say 4, but I haven't written something down yet. That might be a clue. I'm not looking for the number 4. Three. Now you're probably thinking like, what? Why 3? This is where I stop. That is my n plus 1. And I stop at n. So if 4 is my n plus 1, the place I stop is 3. So we get 1, which is the first term, minus 1 over 2, which is the second term, but you added the alternating, plus 1 over 24, minus 1 over 720. And that's our approximation. Okay, last thing to talk about. There are 2 types of convergence. So, suppose we have a sum which converges. We can ask the question, does it converge because you need the plus or minus, or does it not need the plus or minus? So, if we have that the sum with the absolute value converges, then we said it's absolutely convergent. And you can think of absolutely saying, I can throw in absolute values and it converges. If I have something which converges, but when I throw in the absolute values it diverges, then we say that the sum is conditionally convergent. Now, there's a couple of ways you can think about the conditional part. One way you can think about the conditional part is it's conditional on having those plus minus 1s. Okay, so that's one way to think about it. But there's something sort of interesting going on. which says the following. I could take my sum, and remember previously I said when you add, you move to the right. When you subtract, you move to the left. Well, let me put all my positive terms together. That's all the times I move to the right. Let me put all my negative terms together. That's all my times I move to the left. So I have my right movement. I have my left movement. Now, what happens when I have something that's absolutely convergent? That says the amount I move to the right is finite. And the amount I move to the left is finite. And so it doesn't matter if I now change the sign, I still only move a finite amount. Now here's where it gets fun. When you're conditionally convergent, what ends up happening is that the amount you move to the right is infinite. And the amount that you move to the left is infinite. Which means that when you look at your sum, you have an infinity minus an infinity, if you were to break it up that way. And what's true about infinity minus infinity? Yeah, more work is what we often say. It's an indeterminate number. It's an ambiguous number. Now the crazy thing. Because I move to the right infinitely often and I move to the left infinitely often, I can take a conditionally convergent series and I can change the order that you add the numbers. I can still add all the same numbers together. There's infinitely many of them, but I change the order and I can change the answer. Because I can say, look, I start moving to the right until I get to the number I want. I'll go a little bit past it. Then I'll move to the left until I go past. Then I just sort of keep going back and forth. So conditionally convergent series are weird. We always prefer absolutely convergent series. But the good news is we will almost always be in that part where it's absolutely convergent. Really quickly, we have 2 minutes left. We have 1 minute left, but this first sum, negative 1 to the n over 2 to the n, is it absolute or conditionally convergent? So just think about it. I'll tell you, it is convergent. If I get rid of the negatives, does the 1 over n divided by 2 to the n, does that converge or diverge? And how do we know? This is an absolutely convergent because if you throw away the plus minus, what do you have left? It's a geometric series. Negative 1 to the n over square root of n. Is this absolutely convergent or conditionally convergent? It does converge. We talked about this earlier. It's conditional. Because if you throw away the plus minus, you get something which doesn't converge. All right, we'll get a lot more practice with this next time. So next time is all practice, no new ideas. Have a good day.